where we left off. Assuming the lower limit is 0. So we want to write this as an integral. They're already telling us that the a value is 0. Write a definite integral that represents this. So in our limit, we normally had our complete length from a to b. So it looks like that's 2 divided by n equal sections, times by a sum, and it looks like this time the sum is written as an expansion. So a couple of things we can notice, that expansion would be the sum as I goes from 1 to n. In the first one, I is 1. In the second one, if I is 2, it'd be 2 times 2 is 4, then 3, 2 times 3 is 6, until you get to 2 times n. You can kind of see as a hint in the last one where you would plug in the I. So if a is 0, and we have a 2 on the top, I hope you can find out pretty easily that b is 2. And that means anything that you're plugging in will always be, right, this is your a value, which is 0, plus 2 over n times I, and that's what's getting plugged in for your x value. So then it's a matter of seeing if you can see how you could plug this into this equation to find your actual equation. So this is my x. Does that ever appear in here? Yes, this section is right here. Right, there's my x. So can you see that your original equation is 1 over x plus 3? All right, so again, we're going to try to work backwards. We see our sum. It looks like we're going from 1 to 10 of I over 10 times 1/10. Notice the difference in this one is we're not going up to n, and we're not using a limit. If we were going up to n and using a limit, then it would be the actual sum. This time, we only have an approximation because we're only doing 10 sections. But once again, you might notice that your a value is 0. Well, notice you can make your a value anything you like. We've seen that in previous questions. So a nice one is starting with 0. And then, because we've got 1 over 10, which is like 1 over n, you would see that your b value has to be 1. And then a random ui would be a value 0 plus 1/10 of I, And that just replaces this with cos of x. I hope you agree that these are somewhat confusing and abstract already. So would you like to do a hard one? It's like, these are hard enough already just when they're the easy ones. So now what would happen if the exam gave you one that was more complicated? Well, let's look at our next example. Okay. What makes this one harder than normal? Normally you have some number divided by n, because you have n equal sections. Like, they have an n to the 4. So how are we going to deal with that? We need to manipulate this to make this work. Well, we can get our 1 over n if we split up our n to the 4 as a 1 over n and a 1 over n cubed, and then took this 1 over n cubed, and like, I don't like that on the outside, I'm going to throw that on the inside. And then things seem to be a little bit better. I think I'd like to start with a equal to 0. That's like your go-to. If you don't know, if a number a doesn't pop out to you to try 0. It will also work if you use some random number like pi plus e, but I wouldn't recommend it. So if it's 0, well then it's, the number on top is a 1, so it's easy to see that b would be 1. And then your ui is just a plus your change in x, which is 1 over n, times by I. So that's our x value. And if that's your x value, then what's happening is that 1 over n is getting cubed. 1 over n cubed, 1 over n cubed, multiplied by I each time. So this value is getting cubed each time. And that becomes your equation. And we'll go back to our last question as back to a straightforward hard one. Okay? Compute the following definite integral. And again, we are going to learn a shortcut for this. You're going to be able to do this in 3 steps. But we don't know it yet. So until then, what we have is we have Riemann sums and big formulas that we can use. So we want to write this as the limit of a Riemann sum. So we've got our interval from 1 to 3. That's going to be partitioned into n equal intervals, so your change in x is going to be 2 over n. Your ui, your starting point is 1, plus your change in x times I. So if you're forgetting how you get the ui, it's always your starting value plus your change in x, which is just 2 over n, times by how many you have. 1 change of x, 2 changes of x. That's why that I is there. So we can write this with the FU notation. Sum of FUI times change of x. And since the change of x is the same every time, you don't really need that I there, but you could have it. So we plug in our ui into our function. So here is the function f, right here, and we're plugging in this ui in for x. So we get 12 minus, the ui is 1 plus 2 over n to the I squared, because that's what would happen if we plugged it in to f of x, times by our change in x. Now the question says write it as a limit. I probably should be already adding that in. Now we need to figure out the limit as n goes to infinity of this. And now our job is to do algebra until we get our formulas to appear. I should have that limit as n goes to infinity in front of each of those. So we're doing algebra, and our goal is to get these i's by themselves. So we're going to use some summation properties. So notice I've expanded the x squared, then I distributed the 2 over n, combined my like terms, and I've got 22 over n minus 8i over n squared plus 8i squared over n cubed. Technically, I should have this in a big set of brackets. Still have the limit as n goes to infinity in front of all of that. And now it's time for you to give me that guilty look where I say, remember a couple of days ago when I said you needed to have these formulas memorized? And you were like, oh. In those past couple of days, have you memorized them? No, nobody except for Riley. Amazing.
Nice day.
Yeah, amazing. Can I put you on the spot?
No.
No? Okay. All right. Just check. So, if we took that limit of all of these, okay? There's your formula for that one as n goes to infinity. There's your formula for this one. I guess technically, I'm writing things out. I should have that limit out in front. And we do some simplifying. And we're so close. If we break them all up into little fractions, this will make our limit really easy to do. But going back to our limits unit, how many of you remember the shortcuts? Like if you have this, and it's the same power on the top and the bottom, this limit's going to go to -4. And this one, if I multiplied out the top to 8n squared, and my n went to infinity, it's just going to be the coefficient of the 8n squared over the 3n squared. This whole limit is 8/3. I don't mind if you do that shortcut. If you want to show your work, you'd have to do this. But the reason it's just the 4 is because this one, as n goes to infinity, will be 0. And this one, if you did this whole 8n squared plus 12n plus 4 and had them all over the n squared, this is the only one where it cancels out nicely and you're left with 8/3. Everything else is going to go to 0 because the power of n is bigger in your denominator. So when you have big fractions with polynomials on the top and polynomials on the bottom, you can just look at the highest powers, and often you can figure out the limit intuitively from that a lot quicker. So when the highest powers are the same, I have an 8n squared here and a 3n squared there, the limit as n goes to infinity will be 8/3. This is similar to what the strategy you used in grade 12 with rational functions with horizontal asymptotes. You remember when the polynomial was the same on the top and the bottom, so your horizontal asymptote was just at the coefficients. So, I guess technically, oh, how's detention?
Detention. Wait, what is this?
That is my finger.
Okay.
This is for you.
I wasn't in detention.
Oh, I thought you got in trouble with Mr. McWilliams, that's why you did that.
Oh, too happy.
Too happy?
I was singing too much. Thank you.
So all of this for simplification, and then so technically, now that when we take the limit, we just get 62/3. And not too much work at all.
What is even going on the board right now?
Some black ink, blue ink, a little bit of red and green.